that something is dependent on that right there. And nature doesn't like the change. Nature looks at that and goes, wait a second, you're increasing the magnetic flux going into the board. So we need to change that. So we will create a secondary current in the wire here. So there'll be an additional current flowing in the opposite direction. Or as it collapses, it'll be going in the same direction. The same thing as we did over there. So within a single wire, I can also create the secondary current, sort of a back current, which is part of the purpose of something like a solenoid. One, it creates an electromagnet. If I run current through here, I'm creating a magnetic field, but also, as with anything that we throw into a circuit, we're trying to control current. So something like this can keep the current from having drastic changes. If the current goes up too quickly, it'll suppress it by trying to shove a current in the opposite direction. If it's collapsing, it'll try to boost it up. All right, so let's take a look at, I got the solenoid here. I have a coil density of lowercase n. I'm going to run a current I through it. As we've already mentioned today and derived before, the magnetic field in the center, once my current gets up to full power, is going to be mu naught, magnitude of mu naught n times I. Use a naught. Let's see, so let's have this coming towards us at the top and away from us at the bottom. So the wire is coming up this way and looping around like this. So towards you at the top and away from you at the bottom. The magnetic field that is created in it is going to be that way. So this will be a north end and this will be a south end. In an ideal solenoid, the magnetic field outside of it is going to be zero. So what is the induced current? And more, just so you know, my wife has COVID. I don't seem to have any symptoms. However, there are, if you'd like a mask, I'll be glad to go down and get a mask.
You're wearing one, I'll be okay.
You sure? I don't mind going down and grabbing the other box. Do you think you'd feel better with
Yeah.
that? I'll be right back.
Thank you, sorry. Forgot we had class today. I woke up and I was like,
Looks like a lot of people did too.
spring break, how wonderful. And I was like, oh, wait,
Yeah, I'm never gonna relax today.
right,
Let's take it next today.
right. But I'll do it. Yeah, the test and the homework, the only thing. Yeah, that's it. Thank you.
Oh, back over here. So, let's first figure out what is the voltage. what is the voltage that is created by turning this on. We have this hooked to a power supply, we turn the power supply on, my magnetic field goes from 0 to this. I'm not worried about direction. I know that because I'm going from a magnetic field of 0 in the middle to the magnetic field of this, that the magnetic flux is increasing. And because the magnetic flux is increasing, the induced current will try to decrease it by going in the opposite direction. So I'll have a secondary current that is going the opposite direction. So I know that the EMF, based upon Faraday's law, is going to be negative change in the magnetic flux over time, which is the negative change in B dot A over time. For a solenoid, once I turn the power on, this is not going to change a whole lot. This is a stiff enough material, the area is not going to change of any significance. So this becomes negative change in U naught in I times the area. So the only thing that is going to change here is the magnetic field, so that's why that's still after the delta, and I just factored A out. Mu naught is a constant. The coil density depends upon the solenoid. It's going to be a constant for a particular problem. In other words, the number of coils per unit length is not going to change when I run current through it. So negative A U naught in delta I over delta T. Make sure I didn't leave something out there. And we do have to make one other change, and it really depends, you know, I do it differently than the textbooks typically do it. This right here is the magnetic flux for a coil. But in a solenoid, I've got much more coils than that. So really, there should be times however many coils. Because each coil is getting a magnetic field. In an ideal solenoid, each coil gets a magnetic field of this. And so the flux would be the B times A for each coil. So I've got N of them. So throw an N out here. Since little n is big N over the length of the coils, we get negative A in U naught N over L, delta I over delta T. And this would simplify slightly into A N squared U naught over L. So the difference U naught comes first and A goes last. That's an N times the change in the current over the change in time. Ooh, I want to make this a lowercase l. Because I'm about to use capital L for something else. This right here, A, N, and L are all dependent upon the actual coils, the structure that we have. Mu naught is a constant, 4 pi times 10 to the negative 7 decimal meters per ampere. So this is a constant times things that are dependent upon the actual coil itself. This area here is the area of the hole, which is roughly equal to the area, it's the area of basically the loop itself. This is known as inductance. And we use a capital L for that. Let's take a look at some units. Since L is equal to AN squared U naught over L. The units of L would be the units of A. N is just coils. Units of use of knot. Units of L. Well, what are the units of area? SI units. The units of use of knot. And for those who were here, I wrote it on the board.
How about I just can't remember what all the functions stand for?
Check, make sure I did those units right, but I guess it'll come out. And somewhere here, it's in there. That's what meters were in here. And units of, SI units of length. It's not one of those, left with Tesla, meter squared per ampere. Well, let's see if that works out. From our equation, let's see, that would be the units of inductance. Looking over here, this was all the EMF. We have that the EMF is equal to negative L delta I over delta T. What are the units of EMF? What is EMF? EMF would have been last class.
Ideal voltage,
Yes, so what are the units?
the V.
Yeah, volt. All right, so we have volt is equal to, we're seeing if this works out, so we have Tesla meter squared per ampere. Units of current,
Amperes.
units of time,
Seconds.
amperes cancel out, I now have Tesla meters squared per second. Is that the same as a volt? Let's try another equation. Let's see, I know that force is equal to Q V cross D. So if we look at those units, what are the units of force? SI units. In unison.
Is it Newton?
Yes. Newton is equal, and Q, V, units of velocity.
Meters per second?
Yeah. And B, just so you know, these are things that probably good know both. SI units of magnetic field.
Is it T?
Yes, Tesla. So a Newton is a Coulomb meter per second Tesla, so therefore a Tesla per second would be a Newton over Coulomb meters. So that's C and T over S. So if we plug that in for Tesla per second, we have a Newton over a Coulomb meter times meter squared times meter squared. I'm left with Newton meters for Coulomb. What's a Newton meter? Did you say an answer?
I know it, but it is somewhere hidden in
Okay.
the crevices of my brain. Here's a joule.
Yes.
Okay, I knew I would pull it out of somewhere.
So that's a joule per Coulomb. And is a volt a joule per Coulomb? It is. Because remember, if you take the potential energy formula and get rid of one of the charges, we're left with volts. So that checks out. Notice, if I take a look at this equation right here, let's go for the stunning colors. If I solve for seconds, I get CMT per Newton. So we have another unit of time here. The Coulomb meter Tesla, make sure I have dots in there because otherwise it looks like a millitesla. Coulomb meter Teslas per Newton is a second. And you can play around with this enough, and every time a second shows up, you could then, so we could also, from this right here, say that a second is a Tesla meter squared per volt. One of my favorite questions, although there was a flaw to it, was multiple choice, and the question was, how many of the following are units of time? And I have things like this. Now, the reason why it was, the flaw in it was the fact that I wasn't thinking about how much time it would take to figure out each one. And so that was, that problem just took way too long. And also just sort of disappointed at the number of people who did not see the letter S there as one of the choices and marked that one down at least. think that was the psychological aspect of it that I ignored. All right, so, any questions up to here? All right, so we've had capacitors and the symbol. We've had resistors, and that represents a bunch of wire cramped together. We now have inductors. And since an inductor is a coil of wire, that's the symbol for an inductor. So we have capacitance is for example, capacitance equals 4 farads, resistance equals 4 ohms, inductance equals 4. We haven't really talked about the units here, but the unit is the Henry.
This is the one where.
So basic people.
No, we're missing
Oh,
is option.
my wife has COVID.
No,
If you would like a mask,
I did, please. I would actually appreciate it. Oh, no, I thought you meant COVID. It's a joke, it's fine.
okay.
Oh. This is, you said Henry?
Henry,
So this is the one where we could do the Scrabble word one unit.
yes,
Okay.
that, these two both have backwards versions,
Okay.
but not the farad. And then we can play around again with these formulas here and figure out what a Henry is in terms of other things. Just for fun.